Okay, question 3 says find the equation of the tangent line of the curve r equals 4 plus 3 sine of 2 theta at the point when theta is equal to pi over 4. Alright, so just like in the last few examples, right, for this polar equation here, we can consider the corresponding parametric representation for the curve. So since x is r cosine theta and r on our curve is 4 plus 3 sine of 2 theta, x then is 4 plus 3 times the sine of 2 theta times the cosine of theta. And likewise, y is 4 plus 3 sine 2 theta times sine theta. All right, cool. So now to compute dy dx, a little messier here, but it's same idea, right? dy d theta over dx d theta. So differentiating this expression for y with respect to theta, I'm going to use the product rule here. So the derivative of this expression in yellow, right, for r, that's going to be, well, 6 cos 2 theta, and then that's going to multiply the sine of theta, and then plus this yellow expression times the derivative of sine, and that's cosine. Okay, and then downstairs we have dx d theta, so similar calculation there. We're going to get 6 cos 2 theta times cos theta, plus 4 plus 3 sine 2 theta times the derivative of cos, and that's negative sine theta. All right, now you could go about simplifying this, but the one thing you want to keep in mind here is that we want the equation of the tangent line just at one point. So I would recommend that instead of going through some rather messy simplification process at this step, go ahead now and just plug in pi over 4 in for theta to find the slope at this one point, because that's really what we want here. It wouldn't be wrong to simplify this and then plug in pi over 4 for theta, but you're just going to be doing a lot more work than you need to. And note here, things are really nice. When theta is pi over 4, okay, here you're going to get a cosine of twice pi over 4. Well, that's the cosine of pi over 2. Oh, and that's 0. So this entire expression here is 0, and likewise down here, this is 0. And then in parentheses, 4 plus 3 sine of 2 times pi over 4. Well, that's the sine of pi over 2, and that's 1. And so we really just get a 4 plus 3. Oh, that's 7. And so I get a 7 times the cosine of pi over 4. That's root 2 over 2. And then down here I have, well, another 7 from this expression in parentheses times negative sine of pi over 4, and that's negative root 2 over 2. And notice the 7s and the root 2 over 2, all that stuff drops out, and we're left with a slope of negative 1. Okay, so that's really, really nice. Okay, so now to write down the equation of the tangent line, well, our slope, right, that's just the derivative dy dx, evaluated at theta equals pi over 4, and we found that's negative 1. Now, for the point, okay, where do we get the x and the y coordinates when theta is pi over 4? Well, we just go back up here to our parametric equations, right? So if I plug pi over 4 in for theta in this expression for x, we're going to get, well, this is a 7 times the cosine of pi over 4. So that's 7 root 2 over 2. And then likewise for y, that's 7 times the sine of pi over 4, and that's also 7 root 2 over 2. And so now to write down the tangent line equation, just use point slope form. So y minus the y coordinate here, and that's equal to m, the slope, negative 1, times x minus the x coordinate here, and then simplify. Y equals negative x plus 7 root 2. Cool. All right, so then check that out on Desmos. This is an interesting looking curve. It looks kind of like a peanut. Okay, so first notice, right, if theta is pi over 4, okay, we're looking at this point right up here. If we rotate through this angle, pi over 4. So here are the coordinates of the point we're interested in. And then here's our tangent line equation, and that's right there. Sweet. All right, well, that's going to do it. Thanks so much.